So good morning, everyone. Thank you for attending this collaborative event. This is our second additive manufacturing symposium at CVTC. I'm Momu Larudi, Principal Investigator in DREAM Project, sponsored by National Science Foundation. We are bringing people from the community, industry, and high schools to get to know each other and open up opportunities for collaboration in the additive manufacturing field. Based on your response to our question, we chose Zoom as a digital platform to host this event. We are in the middle of digital transformation era, and coronavirus somehow accelerated this process, this digital transformation process. Our world has undergone a radical digital transformation, and in this symposium, we believe there are ways to make it smooth and fun. We would like to use more graphic design and cloud computing techniques to provide you a more enjoyable digital experience. Our aim is to create more interactive and intuitive content, activities like Kahoot with graphical context, digital scavenger hunt in our website, and virtual tour of Zeiss Metrology Laboratory are our first steps in this direction. I'm sure your creativity and reflecting those creative ideas in our surveys will help us to leverage innovative technologies and creative solutions across our online activities. My colleague and friend, Hans Michelson, would share links of those surveys. We have designed 3 distinct surveys for enthusiastic community members, for passionate high school teachers, and valuable industry members. So please click on the right survey that could work for you. So in my end, I'm going to shake your hand virtually by clicking on your names on my screen, and to have a enjoyable digital experience at here. Okay, today's agenda. Mr. Terry Cameron from Desktop Metal will talk about advancements in metal 3D printers, and then Mr. Hans Michelson have some online fun activities for us. The winner of this game and Kahoot activity will receive an Amazon gift card. We have 10 minutes break for relaxation, and then Paul Brackman from Zeiss will give us a virtual tour of their facility in Zeiss Lab. We have another Kahoot activity, and in this activity we have 10 questions for you just to refresh your AM knowledge. And then another break. We will have plenty of breaks to stretch and relax. Mr. Rick Hoyer and Miss Sarah Hoyer from Hoyer Studios will share their experience in entrepreneurship world. And Mr. Joe Warzal will share his expertise in combining reverse engineering and additive manufacturing. And at the end, we have extra time to fill out surveys before saying goodbye. Okay. Dr. Mike Lisecki, our external evaluator, supports us by his survey analysis techniques to have a better understanding of our partners' passion and demographic features of our symposium. And this graph that you see at here shows the percentage of attendees in our last symposium, the first one that we had. We would like to see more orange and gray colors in today's event to receive more support from our community, industrial people, and people from educational institutes. This graph shows the importance of working on initiatives like women in engineering and science. So we are working to invite more girls and women in our event. Our hardworking high school teachers, they are busy, but they joined our event. In our first event, we had 3 teachers, and today 8 teachers register for this event. Hopefully they will be able to participate in the entire event and maybe partially. So At the end, I would like to show you the face and names and email address of our team. We are a small team with a strong passion to develop resources for enhancing additive manufacturing in our region. Now, in this moment, I would like to make Terry from Desktop Metal to be host and then share his screen and start his presentation. Terry, are you ready?
Yes, I'm ready. Sorry, I had to unmute.
Oh, no, that's fine. We are. Now, in this moment, I think you should have, you should be able to share your screen. Okay, awesome.
Okay, great.
Very fast.
So can you still see my screen?
Yes.
Okay, fantastic. First off, I want to thank you, Mahmoud, for putting this together and inviting Desktop Metal to be a part of this. My name again is Terry Cambron. I'm the Director of Sales for U.S. Education, as well as Central and South America. And what I want to talk about in this brief time frame is advancements in metal 3D printing for not only just the education side, but for commercial applications. Brief overview, we are now approaching our 5th year of existence. We decided to come out with a metal 3D technology that was accessible for both engineering side as well as manufacturing. And we believe we've actually done that with the advent of the studio system, which we're going to spend a great deal of time talking about because that's our entry level metal system. Going into the first quarter of next year, we will be making a big splash with our new composite printer called the Fiber. And then on the manufacturing side, we have the shop system as well as the production system that are really geared to those folks, whether they're in automotive or large manufacturing where they're doing hundreds of thousands of parts a week. So these are for maintaining inventories in-house, having customer-ready parts, things of that nature. So like I said, we're going to spend some time going through the studio. So what are some of the challenges that we see in education for manufacturing challenges? Low volume. Almost all parts produced are in low volume, resulting in higher than normal costs and longer lead times. And we see that from both an additive or a subtractive side, where the subtractive folks are not as interested in doing what we call the small batch or onesie twosies, where that's where we really fit the bill, so to speak. Complex geometries. So when you get into applications where you're using 5-axis mills, sometimes it's really hard to be able to actually finalize or finish a part that may have cooling channels that a mill can't do. That's where we come in. Iterating parts, lead times, and machine shop bottlenecks. So these are areas that where we see 3D printing really allowing us to help the end users with the low volume production, producing complex geometries, and again, eliminating the bottlenecks of a system. When we also look at 3D printing, we look at it from 7 different areas: rapid prototyping, part consolidation, complex geometries, design customization, rapid tooling, on-demand manufacturing, and supply chain engineering. But why should a university or a college or a high school teach additive manufacturing today? And it doesn't necessarily mean in just specifically in metal, but even in plastic. Well, first and foremost, 3D printing is here to stay. It is a key technology of design and manufacturing. Some of the larger companies have embraced the additive world, which is beginning to trickle down into the smaller companies. It gives the students an opportunity to learn both from a CAD or SolidWorks and fabrication side, and allows the students to produce parts that really push the limits of manufacturing methods. You know, why should they look at Desktop Metal? Well, first and foremost, we believe that our system, number one, is allows schools to invest in this type of technology. Secondly, we will be moving towards a curriculum and or a certification, which would then allow the students to show future employers that they are able to do the job in both mythology or in the metal side. And it allows them to design and be creative in their current job functions. Within the 5 years, we have now shipped well over, I want to say it's probably about 300 to 350 systems worldwide. Most of them are in the United States. We have a large presence in Europe, and we're beginning to find more of a presence in South America. But if you look at some of the folks that we deal with in the education side, there are some of the big name schools like Duke University, Texas A&M, some of the large engineering, and then even we trickle down even to some of the high schools. Currently, we have, I want to say 2, maybe 3 high schools that have currently adopted this type of technology, which has really been an eye-opener for us, because it really shows that there is an interest even at that level of folks who have an interest in learning this type of technology. On the commercial side, it is much broader. You get into folks that are in the automotive. You get into folks that are in strictly manufacturing. You get into some of the scenarios where they're actually doing a jewelry or what we call a defense, like Lockheed Martin and people like that. So there are a lot of folks that are using this type of technology to better their overall environments. But let's take a look at the studio system itself. The studio system is made up of 3 pieces. You have the printer, which is in the center of the picture here. To the right is the debind system, and to the left is the furnace. So as we go through this, the printer is very similar to an FDM style printer, where we're actually depositing metal powder with a binder or a glorified wax, if you will. And then the other extruder uses ceramic to act as a bridge. So when you center the parts don't center together, and you don't need wire EDMs, or you don't need a bandsaw or cut the parts off. From there, after the parts have been printed, you put them into a debind system. What the debind system does is it removes one of the primary binders from the part to make it very porous. And then the furnace itself is a vacuum furnace, where we're actually getting the parts right to melting point, and then begin the cool down, and then the part takes shape. So there's a great deal of science involved with this, and we feel like we've done exceedingly good at getting parts that have dimensional capabilities greater than plus or minus 0.08 of an inch per inch. We're finding some of the parts that may have simplified geometries that are actually closer to plus or minus 0.005 of an inch per inch. But the build volume itself is a generous 12-inch on the X, 8-inch on the Y, 8-inch on the Z. So you're able to build very small parts to very complex parts to very large parts, in which really sometimes maybe the CNC or the subtractive just really can't do. After this, this material acts the same as subtractive, so it can be tumbled, it can be media blasted, it can be welded. If you want to bring the Rockwell up, it could certainly be hipped, or it can be thrown into an annealing oven to help bring the Rockwell up to make it structurally more sound. So again, this is, instead of taking material away, we're adding, so it does act as the same material as well. Today, the materials that we offer for the studio system is 17.4 and 3/16L stainless, H13 tool steel, 4140 alloy. Copper is being introduced at the end of this month and being shipped out, and then Inconel 625 will be early sometime in 2021, whenever we can get through this pandemic and we can do some more testing. Beyond that, we have a long laundry list of other items, cobalt chromes, other stainless, other alloys that we will introduce as well that can be used within this system itself. Some of the key features when people ask us about why bring metal into it is because they've heard the stories of the lasers where you're dealing with hazardous powders, or you're dealing with the requirements of special facilities upgrades. With our system, there are no hazardous powders. If you see the canisters to the left-hand side here, all of those are the rods of material that the person does not come into contact with. But you can hold the rod in your hand because, again, it is bound metal encased in glorified wax. There's no need for respirators because the debind system uses a non-caustic California Prop 65 compliant solution, in which the operator does not put their hands into the solution. It fills up after you hit start. There is no third-party equipment required. Everything is manufactured by Desktop Metal in Boston. And again, there are no real requirements needed for special facilities upgrades. So we've tried to make it as office friendly as we possibly can. So as we look at some of the applications, so here's a picture of upper left hand of the Texas A&M facility in College Station. Naval Postgraduate School out in Monterey, California, in the bottom left-hand corner, and some of the applications, the University of Maine. And then the one that we talked about, one of the 3 different high schools, this is Diamond Regional Votech High School in Massachusetts, and their ribbon cutting ceremony back a couple years ago. So just wanted to show some of those as well. When we look at some of the applications, this is where we really, I guess, the rubber hits the road, where we're able to really show a differential in price and a differential in lead time in getting something done. This example of a roller screw is about, what, 1.5 inches, 4.8 inches in length, I'm sorry. So you can see that doing it with a laser system, such as SLM, is about $660 to produce that one part. If they do it via subtractive with a CNC, it's almost $2,000. But if you look at how it costs and the time to do it on our system, the material cost and the time to do it is about $86. So again, when you start looking at this, no, we're not going to be the answer for every application, but there are applications such as like a roller screw where this system, our system, fits the bill. And you can see there, that's the application and where it goes into. And it just shows some of the different designs that we're able to make iterations on. And we can also do the screws. And if you wanted to tweak them as well, you could certainly do that. The motor mount. The motor mount is a part that we use for a NEMA motor today. Again, this has been printed in stainless steel 17.4. And again, if you look at the overall costing, we're about 90% less expensive. I hate to use the word cheaper, but less expensive than CNC. And again, the time frame in which it takes to process the part versus the processing of the CNC world is certainly less, and able to get it out into the marketplace faster. And again, here's the bracket that goes on the NEMA motor itself. So people like Baldor or other motor manufacturers can utilize this type of technology, or folks that are using these type of motors that don't want to go back to the OEM but want to print them internally, they can do this as well. One that's really kind of exciting for those students that have watched BattleBots, we actually produced this fighting robot saw arm for a BattleBot at a 17.4. This was really kind of an interesting application that the team came to us. We were able to print it, able to make it pretty by doing some post-processing to it, whether it was polishing or whether it was through doing a ceramic tumbling. But we're able to do the complex geometry that, again, I'm kind of beating a dead horse, but again, that the other additives and subtractives where the cost was just prohibitive for this type of application. Whoop, wrong way. So here is the part here. And this was the group that actually used our saw blade backstop. So again, it was kind of cool to see this on TV and to be able to see the little car in action with a 3D printed part. So then you get into some applications where subtractive just has a very difficult time doing, and that's doing things with cooling channels. We're now printing in copper where we're able to do like a heat exchanger with a cooling channel. And the nice thing, again, is we go back to the ceramic that we use. The ceramic allows us to avoid making this a solid part. So after we go through the sintering part, you can just blast it out with air, or tap it on the table and just let all of the ceramic that has sintered just fall to the desk, if you will. And this is actually a functioning part that is currently used today for cooling fluids. Again, we talk about that it is in copper. And you'll notice that folks like the SLMs of the world are unable to really do this because of the cooling channels and sometimes the material costs as well. Now you'll notice too that the cost of copper is certainly a little more expensive, but when you're comparing that to the CNC side, we're about 1/5 of the overall cost, and the time frame is about half of what it takes for those folks. And again, when you start looking at this, there's a good example of where the cooling channel is being printed, but you are also able within our system to print in both a honeycomb design or a solid. And how that's all controlled is we do it based on where is the stress and the strain going to be put on this part. So we're able to reduce the amount of material and reduce the overall cost by printing this into a honeycomb. And you could certainly change the percentage of honeycomb if you wanted to. Or if we know that there's going to be the stress here, then we can certainly make this section as a solid, making it more rigid in its usage. So here's the part being printed. Here's the part after it's finished printed. We'll then go to the debind and go to sintering, and then the finished part here. Another example of material of H13 where we're using for molding purposes, in which we're actually doing the channels as well for mouthpiece. Again, we're talking about the traditional way, and I should go back and say that the numbers that you're seeing are economy costs from our friends at Xometry. So these aren't numbers that we're just pulling out of the air, but these are actual numbers that we're able to partner with a company to say, what is the cost of if you produce this? So for us, producing a part on H13 and then having it polished or sending it to a finisher such as like REM allows us to make a very pretty part, functional part that again is about half the overall cost of traditional manufacturing. This one is really a cool story for those that are in gas atomization and things of that nature. We work with a company called John Zink in Oklahoma, and they had a problem with being able to come up with an atomizer design that really was able to do what they needed to do. So we went through a number of iterations and we came up with the one on the right hand side. You can see the center one has welds and things of that nature. And then we were able to print it in 316 where it had excellent mechanical properties, able to do the high temperature, corrosion resistance on down the line. And we were able to do this at about 1/4 of the overall cost of what the current process was. And then you could see it's just a picture of it in operation. So that's an overview of the atomizer itself. It has reduced the consumption of gas, if you will, and have been able to spread out accordingly. So they've been very pleased with this. And again, this is just another example of the studio printer in operation today. And then one other applications I think is really kind of cool is with the advent of our high resolution print head, we're able to print parts that are about the size of our finger. So this is an example of an end effector about the size of a quarter that we're printing today. So we're finding that there are very few limitations, with the exception of size, that we're able to introduce this type of technology in today. And of course, we all had to deal with the pandemic. We're certainly still dealing with the pandemic. But what Desktop Metal did is we teamed with hospitals, and we also developed ventilators for hospitals throughout the United States, where we were able to help get low-cost ventilation for those early on in the pandemic with the COVID, and get those out there. And we were able to do this and keep our systems running, keep customer systems running. And this is an example of one of the mouthpieces or one of the components that goes towards the ventilation itself. I want to make sure that I kept us on time. Mahmoud, I hope I did. I feel like I've presented, an hour's worth of stuff in about 20 minutes. Again, if there's something that I can ever do for you, that is my contact information. Please feel free to call upon us, call upon Mahmoud, and he will be more than happy to get you in touch with me. But I want to thank you for your time.
Thank you, Terry. Very, very good. So I think we have time, almost 7 minutes for questioning and answering. So if you have any questions, please let us know. Sure. Yep, Mike.
Terry,
Yes.
I have a question for you, and I asked this in the chat, and both Mahmoud and Hans gave some answers, but what sort of surface finish are we going to get out of these parts? I'm really not worried, but wondering how much post-processing to get that surface finish I might need. How good is it? How bad is it? What's your thoughts?
That's a great question. We print down to 50 micron.
Yeah.
So if it's something that is let's say a non-critical component or a part that doesn't need to be finished, then 50 micron is where we are. If it has to be, then the traditional way of doing sandblasting or polishing or bead blasting glass, whatever the case may be, can certainly be done. How we would go about remedying that is either doing a design change where we may have to add a millimeter or two prior. So you can, when you do polish it off, you don't lose or you don't go into the part itself. But there are ways that we can help smooth out the part, if you will. And there are other ways prior to putting it in the debind where you hit the green part with a little bit of sandpaper just to smooth it out as well. So, but we tell people about 50 micron.
Can you get to 25, or is it no, 50 is your limit?
50 right now is our limit. And that's all based on the particle size, the material size.
Sure.
It's not to say that we can't, just today we can't.
All right, good, thanks.
You're welcome.
Terry, can I add something to your answer? Just recently, Desktop Metal improved their profile. So previously in their Fabricate software, they had standard, and in the standard version, they separated the part from the raft with 3 layers of ceramic. And that 3 layers created some defects in the surface, the quality of the surface. But recently, they released a new option, so you can select standard plus. With that one, they create just 1 layer of ceramic layer that creates more better quality surface finish on the face that part is connected to the build plate. So they are improving their products and their 3D printed parts.
Thank you. Yes. And we will continue to improve. If you would have asked me, would we be able to print those small end effectors 2 years ago, I would have said no. But where we've come in the last 36 months with technology has been a huge difference. And God only knows where we'll be in 12 to 18 months from now.
Any questions from industry members? Are you interested using metal 3D printer in your facility? I know Steve, Mr. Pils is at here. Do you have any plan to use metal 3D printer, Steve, in your facility? Any interest?
We've looked at it. We do a lot of polymer plastics 3D printing, a lot of it, and on the production side of it. We also have a full tool shop, and so we're looking at it and evaluating it, but it's not a decision we've made at this time.
Okay.
And what I would recommend is if it's something that you would like to see a part or a benchmark, then let's have a conversation, because we love doing benchmarks for you. It is free. There's no obligation, so it allows you to kick the tire, so to speak, and see is this something that you want to look at down the road.
Right. We typically have a couple different parts that we run when we're testing any technology with it, and so we can certainly get that looked at and see if that's something we want to dive into.
Sounds good.
Appreciate it.
Thank you.
Terry, we have Mr. Brackman from Zeiss. Their additive manufacturing solutions for inspection and quality check is amazing. They are releasing so many solutions recently on different platforms. So, one of the goals in this symposium is to make connection between different industries. So I would be happy to, facilitate this connection if you like. So in the second section of our presentation, event, Paul will talk about their additive manufacturing solution for holistic, inspection.
Fantastic. I look forward to it. Thank you.
Okay. Hans, do you think we are ready for the next event, your digital scavenger hunt event?
I think so, yes. So one of the things we wanted to do is make people aware of the things we've been doing with our NSF Dream Project grant. And we've been making a lot of curriculum and modules and providing information out here. And so I wanted to, when I first started doing this, I thought, well, how can I show them the website? If I just click through it, it's not going to be too exciting. And so I wanted to make it more of an activity. And so we're actually having a contest, and I'm going to post some questions in the chat. And what I'd like you to do is the first person who gets the correct answer and posts it to the chat will get points for that. And then we have a small prize for the winner of this, I think an Amazon gift card. So I'm going to be posting items. So the first thing I did was I posted a link to the website, and I guess I posted the as down on a page there, but the top level one is the second link there. And so if you're able to open a browser and go to that, I'm going to have some questions here, and then you can see if you can find the answer to these questions. And in order to get it, you have to post it to the chat, because that's how I'm going to tell who got it first. Okay, so the first question is, what was the date of our first symposium for the Dream Project? You have to find the date for the first symposium and post it to the chat to everyone.
Hans, would you like to share your screen? Then you can show if
I can, yes. Okay, we have so we have a winner here. It's August 11th. Angela found it, August 11th, 2020. I think what I will do is, okay.
Angela attended in that symposium, so He knows.
If I share my screen, I will, let's see, I think I'm gonna mess it up. Let me see if I can do this. All right, I will do it this way. And
I think you are co-host and you can share your screen.
yeah, I'm just,
It should be in
okay.
the bottom part, maybe.
I think
In the, this, you know, shares.
I got it. So I think you'll see the screen, and so we have actually our virtual symposium. We have a full recording. We're going to have full recordings of these available on the website, and so you should be able to see the first virtual symposium down here, which was August 11th, and then this one will also be available on the website. Let me see if I got the.
One thing I noticed at here in our website, we update constantly our lessons. It seems that module number 4 metal 3D printer, some PDF documents, we cannot open this, maybe because of the links between website, Google site, and Google Drive. So please accept my apologies for that one. We will fix this immediately after Symposium, but other modules, because I didn't update those recently, they're there, they're good, and you can have access to the PDF document. But the link for videos are available for all modules.
Okay, sorry, I couldn't find my chat for a second there after I shared my screen. All right, here we go. So this is the next question. How many DREAM modules are there? And Angela's got it again. Oh boy. So we're going to go to home, or you can go up to the menu here and then you can see the DREAM modules, and that's correct. We have 5 of them. And so here they are: the Introduction to AM, SLA Technology, Inspection in AM, Metal 3D Printer, and the Innovative AM. All right, we'll see if we can get somebody else to get this one. This one is, what is the name of one of our project-based learning projects, our PBL projects? So we have developed a number of project-based learning projects, and I just need the name of one of them. Oh man, that was close. That was close. So that's correct. Over here we have our project-based learning, and mobile robot is one of them. Also the Kara learning machine, which uses artificial intelligence to train a device, and then the robotic gripper. Okay, I'm gonna do another one. Okay, where on the website can you find the design contest? So you might have to search around for this one. Yes, there we go. So Rick got that one, the Tech Ed Hub. And we don't have it set up on there yet, but we are planning to have a design contest open to the high schools, and additive manufacturing design contest. Did you want to say anything about that, Mahmoud?
So we are working with passionate high school teachers. Garrett Winslow, my favorite teacher, we are working with him, and we have teachers from River Falls High School and from Fall Creek. So we are working to develop contests around AM. So the aim is to use CAD system, design a mechanism, and print parts by 3D printers, and then compare those. So in our weekly meetings, we try to shape this contest. So it is an ongoing process, and we are developing rubric for that. So we are excited. Right now, if you click on the contest, it says the page will be available soon, and we are aware of that, and that probably will be aware in a couple of weeks. Am I right, Garrett? Do you think we can do this in a couple of weeks?
Yeah, I would think so.
Okay, yeah, awesome.
Okay, the next question is, how many lessons are there in the metal 3D printing module? How many lessons in the metal 3D printing module? Angela, again, with 6. That is correct. So if you go up to the Dream modules, you can go to the metal 3D printer, and then if you look at the lessons, there's a lot of, let's see, yes, loading up the introduction, but yes, there are 6 lessons here. You can see from the top, and then if you go down, there are a combination of videos, technical documents, and then we even have activities, introduce the Fabricate software for the metal 3D printer, and let's see down here, yes, and operation, we have a crow's foot design project. So you can do that's a project where you design a tool for the metal 3D printer, and then we can print that tool, and it's a crow's foot, so it'll attach to a ratchet wrench, and so you can design your own tool that can be attached to a ratchet wrench for that one. Joe Vidrosol developed that idea. Okay. Next question. What are the 2 innovation additive manufacturing lessons? The 2 innovation additive manufacturing lessons. So I have one of them. Rick has 1 correct and 2 correct. Okay, Mike Lasecki had the second one. So I don't know, does that question count for 2 points? I guess maybe so. So Rick gets 1, I got, Mike gets the other. Oh, Mike had both of them, that's right. Mike has both of them. Okay, I gotta check the chat there. He's keeping me honest. All right, good. So let me go into there. So our innovation AM, and these I think are not complete yet, but we're going to have topology optimization and reverse engineering. No, they do have, we do have these in here now. So both these are in our sort of our advanced additive manufacturing lessons. Okay, the next question.
We need to provide maybe a couple of Amazon gift cards.
I don't know. Well, we'll see who wins. We'll see who wins. I think Angela's got a lead here, but we still have the Kahoot quiz to go. Okay, next question. What software is used to interface with the desktop metal system? What is the name of software that is used to integrate or interface with the desktop metal system? Fabricate. Good job. So Rick gets that one. And so that's in our metal 3D printer. If you go in there, then you can.
What do you say? You're shooty shooty. I shooty shooty. What do you say?
Yeah.
I can.
Yeah, I can mute Terry. Now we are good.
Okay, and then down here it talks about the Fabricate software, which interfaces with the 3D printer. It goes into the debinder as well as the sintering furnace. So really the same software is used to interface with all 3 pieces of equipment for the desktop metal system. Okay, and we are sort of focusing on desktop metal system here, and here's another question for desktop metal system. Just one type of metal available from the desktop metal system. And you may have seen this in the previous, you have to be specific. You may have seen it in the previous presentation. And Rick has that one. Oh, I think Rick's taking the lead here. Let's see, did we get that? Yeah, okay, so that's correct. So the metals, and they may be, I think we have to get that. You can see it in the videos if you if you are able to get in and watch those, and it looks at the metal comes in these cartridges. You can see it in the picture right here, 17-4, but they can also be, you may have gotten it from the previous lesson or from previous experience. Okay, the next one is, at what point in the metal printing process is the debinder used? At what point in the metal printing process is the debinder used? Oh, and Rick, okay, can you be more specific?
Do you want
Very
him?
good, very good. That's the other part I was looking for.
Okay.
Yeah, so the debinder, so in the metal printing process, you deposit metal particles embedded in a waxy material, and then that waxy material has to be removed before you sinter it. So that's done in an organic solvent, removing those, that binding material. And then it goes into the sintering furnace with forming gas to reduce it and convert it to a solid, finished, hard metal part. Okay, so this is the last question that I have for this section, and that is, what what material is the desktop metal support material made of? So what type of material? Good. Can you be more specific, Angela? Okay, I think I will count that one. So actually it's a bit of a trick question because they have both a ceramic, they put down a layer of ceramic, but then they also use metal supports in their materials. And I don't know if you haven't run the machine, maybe you wouldn't realize that. But they use a combination of a thin layer of ceramic, but then the metal also supports that. So I will give you credit for that one, ceramic. So I'm going to have to tally these points up here. So that's our website. Does anybody have any questions about the website? It seems to be fairly easy to navigate. We have our, one thing I didn't have any questions on the Fab Lab. We also have our Fab Lab on here, which shows all the different equipment that we have on our Fab Lab. And you can see what's here. And eventually, I believe we're going to probably have an interface to schedule jobs. If you're at a high school and you want to run something on one of our pieces of equipment, the 3D printers or the lasers, then you can schedule that, and there will be a scheduling tool available, we think, in the future. So you can schedule it, and then we will run those parts for you. I think that's it. Yeah, well, the other one is we're going to have a magazine available at some point, and that will be available on this website. That'll be a periodical where we publish some of our things that we're doing with the grant. Does anybody have any questions? I think there were some in the chat, so which I think were answered, that there's sort of a ceramic between the metal support materials.
Yeah. Even though we are using metal as the support material, but if this support material, we need ceramic again between in two ends to connect the support material to model material, and in the other into edges of that support material. So I hope my explanation didn't confuse you.
Well, in some cases, you can just have the ceramic material as a support material, but usually if it's any bigger size at all, you have to, the ceramic can't be very tall. And so you need to use the some model material in addition to the ceramic material.
Yeah, my point was just when you use model material as support material, it's still you need to have ceramic on the connection points.
Yes.
If we would like to release that, it makes it easy to release the part. And in one of the videos, the operator shows that clearly, how easy you can just by your hand, release that.
Well, I think we're up to the time for the break, actually. So should we do the break?
Yes. So if you have any questions, please let us know. Otherwise, we would like to have a 10 minutes break at here. Right now it is 9:52, and I think we can start our event at 10:02. Okay?
Sounds good.
Nice.
So it's 11:02. We want to go ahead and start.
Yes, for sure. I make you as a co-host, so I believe you will be able to share your screen in this moment.
Okay. So I'm going to go ahead and share, and then we can get started.
Sure.
So thanks for having us on today. I know I think Pradeep was supposed to give this call to begin with, but he was out this week, so I took over. So hello, everybody. I'm Paul Brackman. I'm the additive manufacturing manager for Zeiss in the US. I'll give a little bit of an introduction on Zeiss's story with additive. And then I've got like a virtual tour that's kind of like a Google Street View of our lab and our space inside of Oak Ridge. So a few years ago, Zeiss started the strategic initiative for additive manufacturing for our entire company. And so that means that our industrial quality group and our research microscopy group are working together to solve what we see as quality issues within the additive manufacturing space. This slide just kind of goes over specific areas that we've looked at and seen places in the additive manufacturing process where there are the need for quality checks and places where Zeiss as a company has some solutions in that space. So of course, this starts all with the raw materials in looking at particle size distribution, powder characterization, even characterizing like raw feedstock in like the wires in directed energy systems. We have systems that can look at those things and do characterization on that. Then the second stop in our blue line is what we call this kind of path, is the in-process metrology and data analysis for powder bed inspection. So this is like an in situ inside the 3D printer. We're focusing right now on powder bed, but we're also developing some solutions for directed energy systems as well. So this is something that is kind of interesting for me because pretty much everything else within the space is something that we already had a solution for. You know, Zeiss has been making microscopes for a long time. Zeiss is making CT scanners and coordinate measuring machines for some time now also. But this in-process system is something that we had to specifically develop just for the additive market. So, you know, we spoke with a few different manufacturers and kind of learned how the in-situ process is currently being done, ways that we can improve on it. And this is a new product that we're releasing. I believe it's next year. Hopefully we're going to show it at the Rapid conference, assuming they have it. And it's just a brand new thing for our company to release something like this. And then, of course, this is while the part is being printed, then we move to the part has been printed, but it's still on a build plate. We want to look at the effects of the heat treatment and part removal on the geometry of the part, you know, how that stress relief when it's cut off the build plate, how does that change the geometry of the part? So we have CMMs and 3D scanners that we can look at the geometric deviations. Then after that, we want to go and look at defect and interstructure inspection. So that's mostly CT X-ray that we're looking at. And then we also do some destructive testing with light microscopy where we cut the part and then investigate it there. After that, we look, you know, once the part has been destroyed with that, we look at the post-print material quality inspection. This is where we're looking at the microstructure of the part itself, and also any kind of like chemical contaminants that we might see in that X-ray CT image. We can go and take that part, slice it at a certain area, look at it under a scanning electron microscope and see what's going on. And then the final part of the process is once we've figured out, okay, we have the defects that we're comfortable with. You know, we don't see any kind of bad contamination. We've already done the investigation of the microstructure. Let's go and start serially producing parts. And that's where we get into the dimensional and surface quality inspection. That's like the final step before we push the parts out the door into service. And that encompasses CT X-ray, coordinate measuring machines for dimensional quality, and then 3D scanning and light microscopy for surface finish inspection. And we kind of tie it all together with a process data statistics and analytics, which is kind of taking all of these things together and looking at the whole chain to say, if we see defects in the powder to begin with, how does that resolve itself with defects in the final part? So since we only have a little bit of time, I'm going to jump straight to the tour of the lab. So when Zeiss kind of came up with this idea for additive manufacturing, we were looking for a space to kind of test all of this out. And we've got some really good relationships with the people at Oak Ridge National Laboratory. So in 2018, we signed a $25 million CRADA with them. CRADA is a cooperative research and development agreement. It's a plan for us to work with Oak Ridge for 5 years to develop tools to solve quality issues in additive manufacturing. So Oak Ridge has this manufacturing demonstration facility that's located on a satellite campus in Knoxville, Tennessee, so just across the river from the main campus of Oak Ridge. And this building here is a 100,000 square foot facility where they invite industry partners to come, bring equipment, and do research with the members of Oak Ridge National Lab. So as you can see, there's a few different spaces in this lab. Zeiss has its own little corner. And if we turn around, these are like office spaces and conference areas where people can come and learn and discuss, research topics. So I'm going to jump straight down to the lab. And you'll see we have this the same blue line here. And the idea for the lab is to be a connected lab for all of these systems to work together. So like we have in the poster, when we start looking at powder characterization, we have a suite of light microscopes over at the window here where we can do transmission light to look at the surface characteristics of the powder. We can look at particle size distribution and check that, during multiple reuses. We're not always looking at virgin powder. We're often looking at powder that's been reused 1 or 2 or 3 times, and how that powder size changes with the reuse, and how we can track that back to defects in the printing process. Additionally, we have a scanning electron microscope here, and then this is an older picture because we actually have 2 scanning electron microscopes here, so 3 in total, that we can also look at powder at significantly higher resolution, actually look at some of the surface characteristics of that powder as well. So the Evo over here is kind of our workhorse. It's a Lab 6 system that we mostly are looking at powder with this machine. This system here is our Crossbeam 550, which is a gallium focused ion beam system. So that means it can image with a scanning electron microscope, but then it has a focused ion beam that can go in and destructively polish away material and then image it again. So in that system, we can do 3D reconstructions on a very small scale to actually look at how that surface and how those features change throughout the print. The other system that we're getting, or that we have that's not in this image, is the same as this Crossbeam. It's called a Gemini, but it's missing that focused ion beam. So it's just a high quality, high capability system, but we don't need 2 systems with a focused ion beam on them. The other thing. Can I ask
you a question?
Yeah.
So on the fib, can you do elemental analysis?
Yes. So all 3 of the electron microscopes are equipped with both EDS detectors for elemental analysis and EBSD detectors for grain structure analysis. And the Evo over here actually has a 3rd detector that's a WDS for more precise elemental analysis. The other system that we actually were a little bit surprised by was this X-Radia Versa system. So Zeiss bought the company X-Radia 6 or so years ago. And the system, if anybody's familiar with X-ray CT, the standard X-ray CT has a source and a detector, and the magnification you get is based on the distance from the detector and the relationship within that space. So it's easy to get, you know, high magnification, but to a limit, because eventually you'll hit the source when you drive your part closer to it. The Versa system kind of combines the principles of an optical microscope with an X-ray system. So instead of just having a source and a detector, you have a microscope on the back side of the detector that even enhances that image to be even higher resolution. And you don't have to worry about getting too close to the source to where you might have a collision. And that enables us to get down to, it's 300 nanometer spatial resolution with this X-ray system. And that lets us image powder directly. And one of the nice things about that is you can actually see porosity that's in the raw powder to begin with. And from what we've seen, that porosity in the powder will then turn out to be porosity in your final parts. So that system, rather than just letting us look at a single slice of powder, we can look at a capillary tube of it and get particle size distribution. We can get shape, and then we can also look at the porosity inside the powder. We don't have a demonstration unit of our in situ monitoring equipment. We're looking to install this next year when Oak Ridge gets a printer that's compatible with it. Right now, we're just looking at, I think, an EOS printer that they're going to be incorporating in the system. We plan for it to be a kind of a machine agnostic thing. So Zeiss isn't partnering with any specific printer. We're not a printer company. We're a quality company. And so the idea is it's an attachment, an accessory that you can put on your existing printer. And right now we're just working with the EOS system. Although I think we're incorporating some other printers as well. So that will be here next year. We're just kind of waiting on them to finalize where that printer is going to go and when it's going to get installed. As I already said, the scanning electron microscopes will do the grain structure analysis of the parts when we're looking at that post-print material quality inspection. But the kind of workhorse for our post-print is going to be the Zeiss Metrotom. So this is a traditional X-ray CT scanner, resolution capabilities from about 7 microns to 100 microns. And it's kind of what we use to image our parts as soon as they come out of the system, when they've been, sometimes before they've even been cut off the build plate. And this system is kind of what we use to look at all the porosity. We can do dimensional accuracy with the system to a limit. Metals are always kind of hard to image in X-ray CT, but the Metrotom's got a 225 kilovolt tube. So we can image like light metals, aluminum, titanium fairly easily. And we've done quite a bit of work on steel and Inconel as well, because the manufacturing demonstration facility is mostly focused towards the metals. They have some polymer and carbon fiber printing systems, but in general, it's all dedicated towards the metals. So the benefit to having these together is that where the Metrotom leaves off in resolution, it stops at about 7. We can go and take that part to the Versa if we need to look at it even higher resolution. That system starts at about 10 microns, then it goes down, like I said, to 300 nanometers. And of course, the size of the image that you're looking at each time is shrinking. So it's not like we can image the entire part at 300 nanometers, but we've done a lot of work correlating images that we're seeing in the Metrotom to images that we're seeing in the Versa, and then taking those images from the Versa. Let's say we see a bright spot somewhere in our part, we can take that into our sample preparation lab that's just on the other side of here, and then go and polish down to that area, and then take it to one of the scanning electron microscopes and image that and figure out where that contamination is coming from, perhaps in the supply chain. So we did a project with Oak Ridge on Inconel turbine blades where we kind of executed that exactly. We're looking, it's Inconel 738, so very crack prone alloy. Routine CT inspection of the parts just for cracks with the Metrotom. inside one of the blades, we see a small contaminant particle, and then we took that to the Versa, found an area that we wanted to cut, found a distance that we wanted to polish down, and then imaged it using the crossbeam to find out where that contamination was coming from, whether it was something that was on the powder side, or if it was a factor of where the printer was in the building and the other systems that were around there, or if it was a leftover from a previous build job. So having the kind of connected lab with all of these instruments working in the same space with this proximity to a sample preparation and this proximity to the printers themselves has really let us speed up the process of doing quality control on the prints. And the idea then is to get all of these instruments to kind of natively talk to each other. Right now, a lot of this is a manual process of me finding a particle and saying, let's go image that one. But, you know, as part of our research and development agreement, the idea is to get them to kind of do this process automatically. Find characteristics that we're interested in looking at from the Metrotome, and then go through the chain to be able to find these in the electron microscopes. So that's the tour, I think, of most of the equipment that we use on a day-to-day basis. We also, and I kind of feel bad because we have our coordinate measuring machine, the Duramax, and we have our 3D projection scanner, which is the Comet. And both of these systems, I think, have a really nice, well, the Comet specifically has a really good place in additive manufacturing for that investigation of heat treatment and how the heat treatment changes the geometry of the parts, how that removal from the build plate changes the geometry of the parts. The Duramax we use quite a bit for imaging or for measuring parts after they've been completely machined, as for most of the time the as-built state of the parts isn't a tight enough tolerance or isn't a precise enough surface that needs this kind of precision for measurements. So we usually use something like the Comet, just get an overview of the system, make sure the print was more or less what we wanted, and then you know, after they get machined, that's when we'd measure them with the Duramax for the kind of the final inspection. So that's the overview of the lab. I saw there were a few questions that came through, so maybe we'll jump over to that. Let me stop sharing, and then I'll get into the questions. How do you handle a record lot traceability in powder bed? So that's been a real challenge to begin with, especially when you're doing destructive testing. If you have a part and then you cut it and then you have two parts now, you know, how do you track that back to what you were getting at to begin with? We've used a couple different systems. We've used some kind of like laser etching. So as soon as the part is printed, well, generally we request that when the parts are printed, there's a build number somewhere on there. Whether it's just built onto the plate itself, you know, just say this is build number, whatever day it is, and then whatever part it is. And then if we're doing destructive testing on them, then we would do some kind of laser etching to know exactly which part goes with which one. Besides that, if they're parts that we can't really put a physical number on, then we use Sharpies, we use bags. It's difficult. If you see, actually I stopped sharing so you can't, on that table there, there's just a bunch of bags full of parts. And it's a very difficult way to do it.
I was looking more for the lot traceability for the raw resin going into, because there's a certain element of recycled powder that goes into each one. So I was looking for the lot traceability back from the manufacturer on the raw resin.
So the way that Oak Ridge is handling most of the printing, so I don't have a lot of hands-on on all of that. What I do know is that whenever they print a part, they take a large sample of the powder before and after printing from the from the powder bed system itself. And I think I don't think they mix batches. So I think they buy a lot and they say, okay, this lot is all going to be for this project. And so they're not mixing batches. They might recycle with the same batch, but I don't think they're mixing batches like that.
Okay, so they're not using multiple lot numbers from the resin suppliers.
Yeah. Is there a learning curve to using the Duramax? There is, but I would say it's not so much a learning curve to the Duramax itself. It's a learning curve to metrology itself. Thinking in terms of tolerances and GD&T and zones and datum features, looking at features of size versus features of form or things like that. I'd say the software that runs it is relatively easy to use when compared to some other softwares that are more like a programming language. Calypso is a very graphically focused software, so you click a plane and there's a plane. But I would say that metrology itself, there's kind of a learning curve to it, and I'd always recommend, doesn't matter if you're a Zeiss customer or a Hexagon customer or Nikon or whatever, the first thing you should do is take a class in GD&T, and that really helps to illustrate exactly why metrology is important and what you can do with it.
Paul, it's Mike Lasecki. I asked that question. It's not the favorite class of our students, GD&T.
Sorry, can you repeat that? Your volume is really low.
I'm sorry, I got to put my microphone down. GD&T is not the favorite class of our students.
Yeah.
It's just the way it is,
Yeah, it wasn't my favorite class the first time I took it, but I took 3 of them.
Yes,
and,
okay.
I liked it more each time I did it. It's very, very dry stuff when you're talking about datum features and tolerances and stuff like that.
Yeah,
but
yeah.
I feel like in design and in quality, it's the most important thing you can do.
All right, thank you, Paul.
Do you find anything interesting about the metal grain structure of 3D printed metals compared to other metals? Yes, and actually I have a slide that can illustrate it better than I can explain it. So give me 1 second. In general, yes. One of the really interesting things that they're doing with Oak Ridge is user-defined grain structure. So you build the grain structure that you need in specific areas. And I don't have an image of that, but I do have an image that kind of illustrates the differences that you see in grain structure in additive versus in subtractive. So this is a light microscope etched image of aluminum tins or aluminum silicon magnesium. And so this is a conventional sample at 100 times. And you can see the grains very, very clearly here. In an additive, this is at 500 times and they're even still really small. And you see these melt pool boundaries, like very well defined, separating these grain boundaries here too. And this next image is a electron microscope here. So you can see you've got this completely different grain structure along the melt pool boundaries versus in the middle. And again, these grains are really, really tiny. So yes, we do see a lot of different grain structures in additive compared to subtractive. And it's been a challenge for us to be able to get good images on these kinds of things. Specifically when we're trying to do like large area EBSD, when the grains are so tiny, then you really have to be tight with your brightness and contrast and your signal to do like a mosaic across these sections, or else you'll lose the entire image. And so yeah, one of the things that we did with the blade project actually was, I don't think I have an image of it either. The blade has a couple different components to it. There's a fir tree at the bottom, then there's the airfoil, and then there's a shroud at the top. And what they were doing with the geometry of the blade there was they're building the fir tree to be more or less equiaxed in structure. And then the airfoil itself, the idea was to build it all columnar and then again build the shroud equiaxed. So you kind of have the properties that you want where you want them. And it's all, you know, the printing is on the Oak Ridge side. But from what I understand it, you know, you change the processing parameters in the areas that you're printing to get the solidification rates that you want, and then that's what determines the grain structure that you get out of the final part.
It looks pretty dendritic at the interfaces here.
Yeah, it's I think this is that. Yeah, this is aluminum cerium, kind of a boutique alloy. But
Does that have anything to do with the 3D file that was used?
Sorry?
Would that have anything to do with the triangulation of the 3D file that was used? Because it looks like in the image to the left, it looks like there's a lot of triangular type geometry.
So I think this would be like a cross section of the interior. So I don't think because the triangulation would just be on the exterior. I think this is related to the scanning strategy of the laser. So I know they've done a lot of work on these solidification rates and seeing, you know, what happens if you just raster back and forth, what happens if you try to do some kind of spiral, what happens if you do totally random just spot points. I'm not exactly sure which method this one was. But yeah, yeah. Are there other questions? Can you talk about CT scanning of 3D printed parts and how are you implementing that into the build parameters? Yeah, let me see if I have a slide on that. So one of the kind of pillars of our Creative with Oak Ridge is rapid recipe development for 3D printed parts. I don't have a slide on it. And kind of what we're doing is we're working with them to kind of speed up the printing process for new recipes. And what I mean by that is they'll print 50 parts on one build plate, every single one of them with a different set of processing parameters. So either different energy density or laser power, speed, spot size, bunch of different stuff. And we're working with them to develop a way to rapidly qualify each one of those and quantify the defect structure of those parts to give a kind of a feedback into saying, these are the best processing parameters for this part, for this geometry, for this machine. And then be able to take that into, okay, what happens if we just bump it up a little bit or bump it down a little bit? Then we can kind of iterate this process to get the absolute best parameters. And then we can also use that to check and see, is there an influence of the machine itself, you know, with the gas flow or the rake direction? If you print the same exact part 50 places on the build plate, do you get the same exact defect structure in the same exact places every time? Or is there some systematic or stochastic expression of the defects? So again, that's mostly using the Metratome. However, we're also incorporating, the idea is to incorporate the Versa also with some machine learning. So image the entire part at one resolution, then use a higher resolution system to confirm or deny the existence of edge case defects, where you think there might be a defect there, but the resolution just isn't good enough in one system. So confirm or deny with the next system and feed that into machine learning to let you kind of extrapolate that over the entire surface or volume of the part.
So you're kind of doing like a DOE on every single part in
Yep.
the different quadrants of the build or sections of the build.
Yeah. I think those are all the questions. If anybody has any other questions, feel free to reach out to me, or you can always email additive@zeiss.com is kind of our group email for any kind of questions about quality, whether or not it's additive. But thanks for having Mahmood, and thanks for inviting me.
Thank you. Very good. So we had a nice conversation with Dr. Pradip Bhattad about this presentation. We knew that there are so many technical jargons in this field, and one of the discussions was related how we can have a sequence of presentation from ZEISS metrology labs to kind of open this discussion. I know you had a very technical discussion with Steve and Hans. Hopefully we will be able to, have this collaboration, invite you in our coming symposium, and help our industry to use your engineering solutions for their engineering problems.
Yeah, thanks. That would be great.
Awesome. So I think if there is no question, we can move toward the Kahoot activity at here. I need to, is there any questions? Any problem, any concern? We are in the middle of our symposium. So it seems that it works. Okay, so I'm gonna activate the Kahoot, and I'm gonna ask you to join this by your phone or by if you have two screens, you can use your computer to do so. Again, this is not designed to check your AM knowledge. This is just to refresh your memory about this field and have fun activity for all of us. Okay, sharing my screen and here. And I'm gonna play this game-based learning. I learned this from our evaluator, Dr. Michael Secchi. Thank you for training us. One thing we learned was this Kahoot has a lot of noise, so I'm gonna reduce this to the minimum. Then this will not bother us. Okay. Thank you, Rob, for joining. Rick and Sarah, they team up. Okay. Very good. Mr. Eric Goldbridge, are you interested in joining this event? Okay, awesome. Welcome. More people, more exciting event, I believe. And please unmute yourself and share your excitement and share your comments with us at here. We would like to learn when we are doing this activity. So after each section, each question, we have a kind of open discussion to share your ideas. Hans, do you think I should start? Let me see if I can see you. Okay, people are joining now. Okay, we may need to wait. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 people are joining. So do you think we are in a good moment to start?
Sure. It's probably pretty good.
Okay. We have Mr. Joe Watersall. He has special talents that here he may, help us to be more excited about this event. Okay.
Last night was a rough one with my baby. She was up all night.
Yes, understandable completely.
That's good. I hope she's feeling better.
I think so. I don't know. Last night was weird. It was like she couldn't get comfortable.
I hope she will feel better soon.
I just hope she'll sleep through the night soon, but it's been 10 months, and some people tell me it could be 7 years.
Yeah, I think that was mine. Or is it 27 years?
Okay, Garrett joined. Now I'm gonna start this. And you know, if you are late, you can join later in the middle. Probably you will not be the winner, but it is worth to join this activity. Okay, our first question. And please let me know if it bothers you or people.
I think your time is a little long for this one, but I think on some of the others, we're going to need that additional time. So,
okay, yes, we have all answers at here. You know, we designed this question to make you happy. Okay. I think it should automatically go to the next one. Maybe because of the color, it was some people click on false. I don't know. Any?
so for those who clicked false, we had true down. Why did some people like false better?
Because everybody's sick of seeing red and blue on their TV screens. That's as far as I'm going with it. I'm not fighting either way. Red or blue, and we're all sick of it.
I was thinking maybe too subtly that 3D printing was a subset of additive manufacturing, but maybe I overthought it.
Yeah, that my first answer was false. And I'm not answering these because I've already seen I know I went through this with Mahmood before. But yes, I would say that it depends on your knowledge of it. If you know a little bit about it, you would say true. If you know a lot about it, you might go with false.
We look at it from the industry impulse around this area, and depending on who I'm talking to at the time is which term I use, because it matters a whole lot. And since my job is to spread it across the entire state, I have to be sensitive to which term I'm using to my audience.
Very good. Very good. So I believe your discussion, your answers is more important than our, you know, multiple choice answers at here. There is uncertainty around these topics. So we appreciate your input. Very good. So Hans, ready for next question? Hans, I would appreciate, since you joined this event, if you just click on one of the answers, so then Kahoot automatically will go to the next one.
Oh, I see. Okay, I'll try to do that.
Okay, I appreciate. Nice. Hans, do we have sound in your end?
Yes.
Okay, is it in a good level?
Well,
not
bad.
Okay. Okay. Yeah, we have 5 correct answers at here. So I would like to maybe show this infographics at here. So we are interested in Deloitte resources. Deloitte Insights has very nice infographics and articles and videos about 3D printing and the trends in this industry. So as you see it here, we have 3,882 AM related patents issued in this time frame. And as you see, it is amazing to see these numbers increase exponentially at here. So just in 2017, there was 749 patents related to this industry.
See, and if you're like most students and you just see the number, you're going to pick a number close to the last number, assuming that that's cumulative.
Mm-hmm. Yep.
Oh, I dropped off the board. Dang it. Too slow.
Paul is coming from industry and he's aware of this trends. That's good. And same thing for Steve. He's from industry.
I just looked at the last answer and I said it looked a little high.
Yes, 7 families of additive manufacturing. Again, I would like to bring this document at here. ASTM F2792 standards shows it is 7 families, and ASTM is very proactive in developing AM standards. Our image may help you to find a good answer. Each time I look at this infographics, I learn new things. Yes, companies. Industry is #1 in this field. Okay, digital light processing is the correct answer. Let me show in the document here. I believe this document. So there are different terms and acronyms for different technologies at here. This document shows with alternative names like this, and that photopolymerization is a technology, and there are different names like stereolithography, and there's another name for this, digital light processing, DLP. So the reason we designed this question was just to get familiar with different terms that different people, companies use. And then last one, I forgot to show information about which sector is dominant in this field. And as you see, company with this color, companies in 90s, 80s, and in this century, again, they're successful in pushing this technology forward and having more patents in this field. Okay.
I think PolyJet uses resin too.
Another document from Deloitte. Yes, 2.7, and we saw that at here. In 2019, this is estimated one at here, and we know that coronavirus affected these numbers a little bit, especially this 2021, the estimated one for this.
I'd almost argue it probably helped it with everybody sitting at home bored and wanting something to do. They probably all went out and bought a little 3D printer.
Absolutely, yeah, I agree with you.
That's what I did. I had one, but I did a lot of 3D printing during the quarantine.
Yeah, but everybody gave all the face shields they made away, so they didn't make any profit.
Mm-hmm.
Just wait till your taxes come around. If you're smart, you'll deduct it.
Nice call. Yeah.
Our presenter after break is Mr. Rick Hoyer. He has used 3D printer, and I think his success story would be a good one. So hopefully soon he will contribute to this number. He brought this infographics from Formlabs. So yes, 2017, I think I can show this at here. Sorry, maybe the text was small, but at here you see it says Desktop Metal introduces the first office-friendly metal 3D printer. And this is the website. This is the resource that we use. So these are OER resources, open source resources. You can type this title in Google and find this document for your references. So high school teachers may like this to provide in their lessons and materials. Industry members may like to refresh their AM knowledge. So we try to have reference for our images here. Brian from industry. Hans, do you think it's a good idea to skip this one or wait for another 30 seconds? Okay, yes. So, fused filament deposition is another name for fused deposition modeling. So we know that these are just terms, but sometimes they are important, especially when you are in an event and in a seminar and reading an article and would like to distinguish these different technologies. So frequently we see FDM and FFF in articles.
I do way better when I just guess instead of think about it.
Yeah, common sense, I think, is very important. It is my number one source, and then, more scientific articles.
It should be fused filament fabrication, I think, is what they use.
Okay. Yes. Yeah. We needed to fix that. Yes. You're right. Maybe two terms for one technology.
So just a little bit of humor for you. When I was working for McNeilis Truck and Manufacturing in Dodge Center, Minnesota, where they build cement trucks and cement mixers, I really struggled to understand what people talked about there, because there was a subset of people from the 70s, there was a subset of people from the 80s, and there was a subset of people from the 90s. And they all had different names for different things on trucks. And they would all say their own name, and everybody understood what they said, except for me, which I heard 4 people say 3 different things, and they all meant the same. Talk about the stress as a new engineer.
Absolutely, yes. Terms are very important, and we would like, based on this survey and feedback from you, we can reshape this activity, have more, technical slogans, or more, focus more on operation and process. We are open to, adjust. And here, the correct answer, as you see, is metal. In average, metal is more expensive. Of course, there are some materials that here, like glass, could be more expensive than stainless steel, but in average, metal is the most expensive one, and plastics are more affordable. Okay. Our last question. Yes, selective laser sintering. We believe it is it has a capability to handle the most complicated geometries. And one of the resources that we use to address this is at here, selective laser sintering. At here, you see the high level of complexities, the strengths of this technology. And we know that FDM has its own advantages. BMD as well. SLA is very good in designing manufacturing complicated parts, and we see it here as well, high level of accuracy and complexity. So we can, the answers are not just 100% sure, high certainty. There are could be a discussion around those answers. So I think now we can see the winner. Winners actually. So Brian. Second place.
What has he won?
Yes,
An all-exclusive paid vacation to his kitchen.
Oh, yay! Do I have to stay there for a week? I'll sleep in my guest room. That'll be a vacation.
It's all inclusive.
2 weeks in quarantine.
Whatever's inside my fridge.
Congratulations to our winners, and thank you for attending. So we learn and enjoy. So if you have any concerns, please share those in chat room. Otherwise, we are going to have another break, 10 minutes break. Right now it is 10:57. Let's see you at 11:07, okay? See you. Okay, welcome back. Mr. Rick Hoyer and Miss Sarah Hoyer from Hoyer Studios. Rick graduated from Mechanical Design program with many achievements, including winning a national design competition sponsored by SolidWorks company. So Rick and Sarah, I would make you as a co-host at here, so you will have a chance to share your screen and start your presentation. Thank you for being in our event.
Thank you.
Yeah, thanks for having us.
All right, let's get this started.
All right. My name is Rick, and I'm from Hoyer Studios. And with me is my partner, Sarah. And as Mahmoud had mentioned, I am a 2020 graduate from the CVTC Mech Design Program in River Falls.
Hi, my name is Sarah. I'm a senior at UWRF majoring in art history. I'm also the marketing and design specialist at Hoyer Studios. Together, we placed first place at the 2020 ATA National Design Competition with our mobile robot that we call Mary.
Because of this win, it has inspired us to take this robot to the next level and develop an outdoor mobile robot that has capabilities to mow grass and blow snow. Our printer is a Zortrax M300 tool FDM printer. It has build area of 265 by 265 by 300 millimeters, and it's capable of printing with 10 different materials. It came from Poland, and what I find is the technology in Europe is very similar to what it is here. It just uses different terminology. I think it's an effort to be proprietary, I guess. The first robot we built in school, we used the 80-20 T-slot extrusions. My original idea for manufacturing a curve was to bend bar stock and weld the extrusions to it. We then realized in class that additive manufacturing would be a much better solution. And the picture on the right is the curve for the outdoor robot, which will be done the same way. Additive manufacturing has been a great alternative. We've had our 3D printer for a few months now, and I've been exploring with it ever since. Our first experiment was to determine its accuracy, and I printed the puzzle block and then the wrench. Mahmoud was kind enough to forward me a study done by Formlabs to determine gap sizes between components. These were just guidelines, and each printer is slightly different, so a little trial and error is in order.
We definitely really enjoyed the jokes that were going around about buying 3D printers during the pandemic, because that's definitely what we did, and that's what we've been working on mostly throughout the last few months.
I actually got nearly 900 hours clocked on it, and we didn't have it up and going until just about August. So it runs pretty much. All right, the next, we started exploring with different materials. The third part, previous slides, was printed with at 10% infill with a product from Zortrax called Z Ultrat, and material that is very hard. It is so hard that I was unable to crush it in a vise. Then we tried the flexible material from Zortrax and printed air cushion insoles. It took 5 prints to get them so that they were comfortable. I was also able to find an app that you can scan your foot using your cell phone. It can give you all the measurements for shoe designing.
We then tried multicolored printing. Our first attempts were unsuccessful because the different colors that we had available were of unlike materials and they wouldn't adhere to each other. While it turned out pretty cool, it was very labor intensive. We tried to allow 2 to 3 layers for each color and then calculate the time required to perform the task, pause the print, then change the color and restart the print. We also found that it is incredibly important when designing to be mindful as to which colors are applied over others. For example, the blue or black filaments are too dark of a color to be printed first because it tends to show through red, yellow, or white. We could print them first, but there would have to be more layers of the lighter colors so the previous shade wouldn't show through.
The main reason we purchased a dual extrusion printer was to be able to print assemblies. As you know, the PBA dissolves away, and exploring further, I found a website that suggested allowing 2 layers into the design. 2 layers did not work on my printer. So I adjusted the slicer to its thinnest layer thickness, which was 0.15 millimeters, and allowed for 3 layers, which ends up being 0.45 millimeters, and then became successful. When it came to large prints like the gearboxes and gears, we set the slicer to the thickest layer height, which is 0.30 millimeters. I have learned it shortens the print time considerably, with practically the same results. The gears are quite accurate and work quite well for being plastic. And the ones you see in that actuator, linear actuator, I've had up 2,000 RPM, which is pretty fast without wrecking the gears. I found it necessary to create little half-hour test prints for fitment, and nothing's more disappointing than realizing your 25-hour gearbox print that the bearings were either too loose or too tight. Some of the current challenges we have in additive manufacturing is reverse engineering and 3D scanning. We are also experiencing difficulty with prints being warm enough now that the weather has gotten colder, even though we have a fully enclosed printer.
We are also playing around with photogrammetry as a 3D scanner for reverse engineering. Excuse me. We're also playing around with photogrammetry because a 3D scanner isn't, for reverse engineering, isn't exactly within our budget. We have had mixed thoughts with this, as masking the 50-odd photos is pretty time consuming with results that were not always consistent.
Does anyone have any questions for us?
Very good presentation. Thank you, Rick. I think our Fab Lab, we have 3D scanner, very advanced one. Zeiss manufactured that. So if you have any question, Paul from Zeiss is at here. He may help you. Our Fab Lab is open. You can use it. We have so many resources. Joe Weierzall, he's our hero in reverse engineering. He can support you. And we are at here to help our local industries, especially startups like you, to go forward. Yeah.
And we might have to take you up on that too.
Pardon me, what was that?
I said, we'll have to take you up on that offer.
Okay.
Any questions we can answer?
I have a question.
Yes.
How did you build up a customer base for your, what can you describe how you build up customers for your business?
We started out with a website, and and it's amazing because we developed a few different products, and Sarah seems to find friends and things that we can build things for.
Mm-hmm.
And I have a design horizon myself that seems to be never ending, so I come up with new ideas all the time.
And I connect a lot with people who follow us on social media, and friends of mine who have friends who have friends who have friends who are interested in different products that we can create. And by word of mouth and through social media and our website, we've been getting in plenty of clients.
Well, and
Nice.
I would like to get out there more.
Mm-hmm.
And if anybody has any ideas on how to make that happen, I'd be willing to collaborate with them.
Interesting. Thank you.
We are just, we have time for
It's up to us.
questions. If there's any questions.
I think Mike had a question in the chat. What do you say if a customer asks for a metal part?
Well, I guess then we have to refer it to the CVTC.
Yeah, unfortunately, we only have the plastic 3D printer right now, but we haven't had anybody ask about metal parts so far, but I'm sure that's coming on the horizon as well.
I see that there are plastic-based filaments that have metal particles in it that are being developed, and I'd be interested in explore with that at some point also.
Our, again, Fab Lab is open for your ideas to explore. I believe John Onefeld, we use our SLA 3D printer for him, and he said, okay, this material is not resistant on some environments, like when we have acetone and alcohol, this material will not tolerate. So we need metal one, and we are going to print his part in metal with our studio system. So again, this is available for you, and you can use our resources. We are a public school, public institutes, and our goal is to not only develop resources, but also support our industry members.
Mm-hmm. Absolutely.
Yeah, many components for this outdoor robot are going to be done with additive manufacturing, and I'd be interested to see like gear sets, how they could be done on a metal printer. I don't know what would be required for polishing, but it'd be interesting to see.
Yep, especially for customized parts. I believe Desktop Metal was successful in using metal 3D printer for gears and gear manufacturing. Again, probably not in mass production manner, but in more customized one for prototyping. They have like products like production that you can manufacture hundreds of parts per day, but we do not have that equipment yet in our program. In the future, based on the supports that we may receive from National Science Foundation, we can offer that service to you as well.
Can parts on the Desktop Metal, can they be polished without removing too much material?
I am not expert in manufacturing area. Hans and Joe might be able to answer this. They released a new option recently that it is the surface quality is good, but I'm not aware of the techniques that can just maintain the material without losing those. Hans or Joe or other industry members, you may have some ideas for this question.
I'm not sure. I'm going to defer.
So last year, when we were able to get through the full process, we were able to 3D print with the metal 3D printer. We did find some deformation, like they talked earlier about, the tolerances after you go from printing to debinding to the oven. We did polish. They did polish up good. Amount of material that the student removed, I do not know. It didn't seem like a lot. But to get better surface finishes, you are able to polish, but you got to remember the output of these parts coming out of the metal 3D printer are going to be more of a cast type grain structure than a solid steel type structure. So you're going to have porosity and things, in there that you might find.
Were you able to break the gears?
We didn't print gears. We were just printing random parts and stuff.
Gotcha.
Yeah, it would be interesting to try some heat treatments like a quench or surface hardening or something like that and see if you could work on it. Mike has a comment. I think you can go.
Hans, I think it was Paul that might have said that in the design, you can add a bit of thickness to the surface that you want to polish to accomplish, you can't always do that, obviously, but that could compensate for the material removed by polishing. I think it was Paul that said that.
Yep, I think you're right.
Yeah, I mean, if you know that you require certain surface characteristics, you can always overprint them.
Yeah.
Or you could change the print parameter. If you don't need a fully machined surface on there, you could print with specific contour parameters that can really get you nice surface finish at the expense of usually a little bit of surface porosity or subsurface porosity.
Sure.
Yeah, we never really got that far to play with those parameters, but as always, it's metal, so it's going to be better than most things.
We have a lesson in our modules like design or manufacturability, and this is for additive manufacturing. I think we are developing constantly, and we are updating those. This would be a nice topic that we can add to this DFM for additive manufacturing, and then I'm going to share that with you and with entire members at here. Maybe address that in our their symposium, and talk about how we can, as Paul mentioned and Mike mentioned, have that extra thickness in mind in design process, and then after printing, we can remove those. So very good. This will be a new update for our modules. So very good input from industry. Thanks.
Absolutely. If you guys have any further questions, I'm going to post an email in the chat group. So if you guys have any questions, feel free to email us.
Sure. Very good. Okay, our next presenter, Mr. Joe Watersall, has a strong background using metrology equipment. He will talk about his achievements in this ever-changing field. So, Joe.
Yeah, so I don't know if everybody was on last time, but I kind of got my start with types of scanner and photogrammetry and those types of processes when I was working for McNeilus, when we were looking for a way to inspect dies for stamping drum fins for inside of mixer drums. And that kind of got me down the road of reverse engineering and inspecting. So I'm not going to take too much time. I know we've been on here a long time and it's Friday and, you know, everybody's stressed out, but I just kind of talk a little bit about some of the stuff we've been doing, using the Zeiss scanner to take parts from the real world, which this is not coming out very well. Let's see if it gets better when I get really close to me. Can you see it now? Let's get rid of the background, maybe.
A little bit difficult to see that, but
I'm gonna get rid of the virtual background.
Yeah.
Let's see. None. Okay. How about now? Can you guys see this now?
Yes, so much better.
So this is a just basically a nail gun that Ashley Furniture uses, and I don't know exactly what the reason they wanted it for, but I'm assuming they want a model of this that they can use for their design group, so that, you know, when you talk about DFM and somebody designs something really cool and then I can't get my nail gun in there to nail the two pieces of wood together, right? So you look at this thing as a designer and you say, hey, you know, I can draw that. And then you start drawing it with a micrometer and a caliper and you start doing all those things and you realize, holy cow, this is going to take me like 80 to 100 hours of straight CAD time to get a good working model. So with us here at CVTC, we've got the scanner and the skill sets. So I'm going to share my screen now, took this tool. Let me know when you guys can see it.
Looks good.
Okay. So we took this tool, and in the software, the proprietary software that we received from Zeiss for scanning our point cloud, this was our end result. Looks pretty cool, right? If you zoom in here, you can see how detailed the scanner is. You can read the oil label here on the back. If you zoom in, you can read the warning label, right? It's a pretty powerful tool, but when you look at it, you're like, holy cow, there's a lot of holes in this point cloud, right? So we purchased another software from SolidWorks, or whatever 3D Systems, whatever the parent company is called. My brain, Geomagic Design X. So we purchased this reverse engineering software to go through and create 3D models. So as you all know, scanning can take some time, but once you figure it out, I was able to scan this point cloud here in the course of about 3 hours. And that was probably 15 minutes of me setting up the rotary table and letting the thing go and take picture after picture after picture and then rotating it. So once you go through this this process of cleaning and filling holes and, you know, cleaning up this this picture, which is, I'm just do a quick little kind of a little synopsis. You can come through and like pick these surfaces and fill these holes. Takes you maybe a couple hours, and you can smooth your polygons, and the software allows you to output a model right into SolidWorks. So I'll open up SolidWorks and I'll show you the surface model. Maybe I'll show you the surface model. Can you guys see the surface model pop up? No? I'll share again.
Yeah, I could see it.
Oh, sorry.
We had it for a minute, but it's gone.
Coming
Okay.
back.
Back.
It's coming back, hopefully.
Yeah, we can see it.
I mean, it's really rough, but once I cleaned up that point cloud, which took about 2 to 3 hours, I was able to output this rough surface, right? You know, I don't know how much information or detail they need, so I'm not going to spend days on this. But I was able to output this 3D model surface and made it up accordingly to the coordinate system and create a physical model that they can use within their design department to validate and understand design for manufacturability. So I made a little video here. Let me know if you guys can see the video here. So that the designer can use, you know, physical data to create working design models before you go to build something, right? I know in my previous life, when you're building a $500,000 chiller and things don't go together, people get kind of mad, right? Leaders and VPs and people get upset. Well, you know, with these tools, we can do some pretty amazing things. Now, we're talking about additive manufacturing, right? You know, they're really not going to 3D print. They're really not going to 3D print this part, right? Because they have a physical part. But now let's talk about how we can take that scanner and go to a 3D part, right? So there's a local company, and I talked about last time about 3D printing parts for classic cars and stuff like that. So I wanted to kind of show you kind of the steps in the scanning process and going from a scanned part, which looked like this. So this was the original part coming. Oh, I'm not sharing my screen. Somebody's got to stop me. No one stopped me.
I can see it now.
Okay, so this is the original part, right? So this is our scan data, our point cloud, right? Very detailed. If I turn this over, I can see the part number from Ford Motor Company from 1960, right? Very detailed, very good at inspection. And then I could take this straight to a 3D printer and reprint it once I create my STL file. But let's say I want to make some changes on it. Well, that's where this software comes in. And over probably a couple hours, I was able to smooth this out, fill the center hole, create some surfaces and some extruded parts, and I could create the future shape of that part. If you look over here on your design tree, there's 1, 2, 3, 4, 5 things that are just like SolidWorks. And if you're much into designing, 5 features in the design tree is pretty simple to create and pretty fast. And the software is so powerful that it'll automatically create sketches for you, which is wild that you can do this out here with some softwares. Just go out here to this mesh sketch, pick your plane, and drag your plane through the part. You see that blue line right there? that blue line turns into a sketch that you can automatically use to model, to extrude. So if you want to take something, modify it, and go right to a 3D printed part, in less than a day, you can take something from 1960, scan it, reverse engineer it, change it, output a part, and put it right into a 3D printer. So I'll just quick show you here the next step, right? So once you're done in that software, you can output your part right into SolidWorks. And what the software does is it gives you a smart part. And in the past, us as designers always struggled because the output of laser line probes or scanners or photogrammetry was dumb parts, where there was no design tree, there was no features, it was just raw pixels and polylines and things that you couldn't do. But now, with the ability of these softwares and the scanner, you can output a physical solid part with actual cuts, extrudes, and features that can be saved as an STL file and dumped directly into your 3D printing software. Right, so I just wanted to kind of show you how we were able to take this original part and shape, scan it, modify it, turn it into a smart part, which somebody can modify even more in the future, and dump it directly into a 3D printing software. So this, in less than a day, can be into our printer, right? Obviously, it's going to take time through the printer, but in less than a day, you can go from nothing to a point cloud to surfaces, sketches, and extrusions to a final part in SolidWorks or Creo or other softwares, and then directly into your 3D printing software. So I just wanted to kind of show you that, and then open it up to questions, right? You know, we've been here 3 hours. You know, if there's questions that people want to see, like specifically, how do I fix a point cloud, or how do I create the surface? I just wanted to leave that out there for people to ask.
Is this a service that you perform?
A service that we perform. Well, we partner with our industry partners. Well, we have industry partners, right? So Ashley is part of this additive manufacturing project, and right now, like, I'm the instructor, I'm partnering with them, and to create these types of tools and these outputs. In the future, the goal is to incorporate these into the capstone class, where, say, somebody comes in and say, hey, I want a 3D model of this. We can make that part of our capstone project where students can work with a company and create these things. So it's more of a partnership than service, but yes, we work with the industries that are supporting us, like you on this call, to do small projects like this. Who asked that question? I'm sorry.
That was Steve.
Yeah, there's a question from Mr. Hoyer at here. He asked, how do you repair a point cloud?
How
do you repair a
we've been
point
working
cloud?
with 3D flow, with photogrammetry, and that was one of my biggest problems that I was having, was repairing point cloud.
Okay, so the short answer is, or the long answer is, or no, how do I best say this? Yes, you can repair point clouds, and yes, there are softwares out there, free softwares you can download to do that, but you really need some of these specific softwares to get good point cloud cleanup done. And that's where Geomagic Design X comes in. And for instance, right here, if you look, this was a paint chip in the surface of the part, right?
Yeah.
And technically that could be a defect, something you want to clean up. And in this software, it's as easy as coming up here and click the D feature tool. And I come out here and I just lasso that region. And over here in my feature tree, I can tell it I want to fill it. I want to match the curvature of the area. And I click OK. And it's as simple as cleaning up your point cloud that way.
Oh, that's
Now,
pretty handy.
yeah. Now let's say you have a hole in your point cloud, right? So let me just delete some stuff here. So let's say I have all these holes in my point cloud, right? But you get these holes, and I zoom in, and I've actually have the points turned off right now and just have the STL features on. But this software also has a fill hole tool, right? And you can change tangency, curvature, flat, and you can come in and select these holes, and you can fill those holes. So like you can see, I deleted that area out, and you're able to fill it in, right? You can come in and smooth, right? So they make these smoothing, cleaning, and enhancing features, right? So you can come in with like a paintbrush and just clean up areas. So, yeah, so these softwares are set up really similar to design softwares where you as a designer can take point clouds and clean them up and fill holes and stuff like that.
Oh, that's a great demonstration. Thanks.
Yeah, and the only free software out there that we've been able to find is called Mesh Mixer. And all Mesh Mixer allows you to do is pretty much fill holes and smooth.
We've been using 3D Flow.
Okay.
We saw it demonstrated through a college art program, and it was last semester when they were having to photo scan their projects and send them to the instructor, and doing it that way. And I thought, well, that's kind of interesting. And I thought, well, maybe we could learn how to do this, but I found it to be actually pretty difficult. You know, you have to mask all their photos. You got to take 50 photos and then mask them all. And like you say, there's a few hours of work involved, you know?
Yeah. And that's the beauty of like the Zeiss Comet and the rotary table is, you know, it's taking pictures and creating that point cloud and allows it, and the software is smart enough, as long as you tell it, you know, what features are common, it'll automatically align all those for you.
Yeah.
Blender is a freeware open source software that you can manipulate point clouds with, although it's more for artistic purposes rather than engineering purposes. And it's pretty difficult. It was fairly difficult for me to try to figure out how to use it, but it's free and you can do some smoothing and stuff. So if you don't have the money for the Geomagic, which I think is sort of expensive, Blender is a free one. It can do some things.
Good to know.
Yeah.
Geomagic is free for a 15-day download. And they have 3 versions of the software, so you can step up and get 45 days of all their software.
How would you rate the learning curve for Geomagic, Joe?
If you know SolidWorks, it's very simple to catch on to. So I've never been trained on the software. We purchased the software end of last year. and this is kind of unfair because I did go to training on Polyworks, so I understand the principles of all these steps. I just don't understand the clicks. So by knowing SolidWorks and the background of Polyworks, I was able to pick up this software in about 3 hours.
Very good.
Nice.
Any more questions?
Very
So,
good.
one thing I do want to show you guys, though, when we tried doing this work before we bought this software, like we were doing the artistic stuff, we were having a lot of failures in our 3D prints. And one thing I found is, so 3D printers use, you know, STL files, which is basically, you know, triangles all meshed together. And if you don't know what to look for, you can create defects in your parts. And the first thing that we found, where is that part here? The thing, oh, I gotta want to import, is if you're just playing with like these free softwares, you gotta like cross-section your models to make sure there's no triangles bridging between like your top surface and your bottom surface, because your 3D printer will technically not create a gap, but it'll create a defect like porosity or lack of fusion through your part, right? So that's something we've learned here in the last couple days. That is pretty important. See if I can find the part I'm looking for.
Yeah, you can corrupt your parts pretty significantly if you aren't careful, where you have, you know, 5 points all at the same point, so there's really no triangle there. All kinds of weird stuff that can happen with those point clouds.
So I can't find it right now. It's on. Something's going wonky with my my computer, or my jump drive and computer. The software shut down on me, and you know how it is when you're under the microscope and you can't find anything. So any other questions out there?
Steve, I think I interrupted you when you wanted to ask your question. Did you have a question? No? Okay.
No.
Nice.
All right.
Thank you so much. Very good. You are collaborating with Ashley Furniture, the world's largest furniture manufacturer. So this is very good.
I haven't heard back from them if this is what they wanted, but I've sent them the part. We've got the scan. I don't know if they want it more detailed or not. But this simple surface took me about, I don't know, a couple hours to create.
Paul, we are very interested in using Comet 3D scanner for inspection as well. So as you see, we are successful using this device for reverse engineering. So do we have any chance to receive support from you? Maybe a presentation about how you're using this device for inspection purposes?
Yeah. I don't have anything right now, but like we've used it. We're currently working on a project to do this this mapping of deviations from the heat treatment process and removal from build plate. We had a project where we knew the parts at the end were going to be machined, and so additional material was being printed on the outside as sacrificial, so this would be machined away. And the group that was doing the machining had trouble finding the machine part within the preform, so they ended up growing that surface by like 200%, which adds a lot of time and cost to the job. So we're working on a project right now with the Comet to try to, one, shrink that part, and then two, understand what happens when that post print heat treatment and removal from the build plate occurs. So yeah, I mean, it's definitely something we can share when we have some results from it.
Okay. Very good, thank you. Now we are approaching toward the end of our event. We would appreciate if you could fill out the surveys. Hans shared those in our chat area. So we have 3 distinct surveys, one for industry members, one for high school teachers, another one for community members. So this, your inputs will help us to shape our symposium in a way that works for you.
And the industry one is for the questions specific to the advisory committee. So you could also fill out the attendee survey, because that has, I don't think there are any questions about this symposium or the presentations here in the advisory committee survey. So if you want to do those 2, you could. If you're a teacher, do the teacher survey. And you could also do if you're a teacher on our advisory committee, you could also do the advisory committee survey and the teacher survey, I think is best.
Okay.
What if I want to do all of them? And it
works.
No.
You're not allowed to do all of them, Joe.
I think, yes, we like it.
Doing any.
You do have to do one of them, Joe. You'll
know,
know. We know if you did it or not.
Joe actually gave us a very good input about Kahoot last time, and we fixed that problem. Yes, we had 30 questions for Kahoot. He said, no, just 10, and we listened. So
are we going to give 2 prizes, Mahmoud? What do you think? I wasn't sure how to score these now that we got down to it here. We had Angela won the first in the scavenger hunt, and Paul was first place in Kahoot. I don't know.
yes, I think we need to provide 2.
We might do 2 prizes. Yeah. Okay, we'll announce those later, I think. Or I mean,
yes.
Send them out later.
Yeah, I will share with you the, probably I can mail the Amazon gift card to your address, or I can send just a number, the voucher number or the code with you. So you can.
I would just send out a digital card.
Okay.
Yeah.
Sure. Okay. This time, 11:45 to 12 is just for giving you a chance and time to fill out the survey. So if you have any comments, inputs, please let us know. You are at here until 12, and talking about, having conversation about anything.
How many more of these are we doing, Mahmoud?
Pardon me?
Are we doing more of these?
Yes, we will do this quarterly. So the next one will be around February.
So, okay.
The NSF wants us to collect data on these. That's what the survey is for. It's to support our grant, and we use this in our annual grant report. So we really need as much data as we can collect on who's seen this and how they're using our material, stuff like that.
Okay. FYI, if anybody's interested in an Amazon hack, if you're buying a commodity thing, and let's not say a commodity thing. If you're buying like a off commodity thing like a CD player or a light bar or something that they have at Amazon, Amazon will have an algorithm that says how much do I think this person is going to pay for something. And I found this on many times where my friend who doesn't have an Amazon account will tell me to order something and he'll send me a screenshot, and his item is $1 less than what mine is. So I never go to Amazon logged in. I always fill my cart not logged in, and then I log in.
So as you see, we provide information not only about but also purchasing technique.
Thanks, Joe. All right, are we done?
Very good. So thank you so much for attending. We appreciate that. So have a good weekend. Enjoy your days and see you in our next symposium. I will share more resources with you soon. Thank you, everyone.
Okay,
And
thank you.
Mahmoud, can you ping me right after this?
Sure.
Sure.
Thanks, everybody.
Thank you,
Yeah.
Paul.
Bye.